check. Okay. So this talk is based on a blog post of mine that I wrote a couple of weeks ago, based on a couple of design decisions in Hashable which I object to. And I would just like to give you a quick overview and then an introduction to what I think could be improved for Hashable and why. In particular with the looking at Swift on the server. So, but first to get on the same page, let's first look at what actually is Hashable and what it is for, what it is needed for. And so an easy elevator pitch of Hashable would be that it helps hash tables and hash maps, which are the basis of both set and dictionary in Swift, to find values very efficiently without touching unrelated elements. So you don't have to move or walk through a long list of elements to find the one you're looking for, because you already have some kind of heuristic of where to look for the stuff you're looking for. And if you want to visualize this in a very reduced and simplified form, you could imagine a hash table being a simple table with indexed buckets, and each of these rows is basically a list of possible elements. And pardon me. And if the hash value of foobar would be 3, then you would know that 3 would have to be inserted in the third bucket, or fourth bucket actually, and you could then just add the element to the list in there. Or if you want to look up the element and check if there's actually foobar in the given set, which is realized by a hash table, you would just look in this row, and you wouldn't ever have to touch 0, 1, 2, 4, 5, and 6. So that's the benefit of hashing, among other uses like cryptographic hashes and stuff like this. Again, this is oversimplified. Usually those are much more difficult, but this should get us started for the purpose of this talk, which basically is about hash value, not so much about hash tables. So to give a motivational example of using Hashable, imagine you're writing a Minesweeper, and you want to persist the location of mines as well as the fields you already cleared or flagged. So one way to implement this would be to use a struct for grid points, which have their x and y coordinates, as well as a class for Minesweeper, which then has the grid coordinates, the mines, the cleared fields, and the flagged fields in sets, respectively. If you had a big canvas, you would probably not do it with sets, but you would instead use some kind of bit fields or bit vectors. But for this particular example, this will work. And if you try to compile this, you get these two compiler errors, which basically tell you that grid point is not equatable and isn't hashable either. So equatable is pretty simple. You just implement equatable the way you would implement it for pretty much any other type as well. You just check those fields for their corresponding values in left and right-hand side. So that's one gone, one to go. And for Hashable, it's a bit more tricky because you first have to figure out what actually makes a hash function a hash function. And for this, it's good to look at some of those key properties of hash functions. One of them being that hash functions map from a variable-sized input, or at least potentially variable-sized input, like strings, for example, which could be arbitrarily long. It could be just hello, or it could be the entire script of a movie or something. And you map it to a fixed size output value, 64-bit integer. The second one is that the mapping behavior has to be persistent, or you could call it functionally pure. You always have to return the same return value for the same input, at least for the time your application is running. Between different application runs, you can have different outputs. So it could return 42 in the morning and then running it again in the evening. with quitting the app in between, it could return like 12 or something for the same object. But as long as it returns the same hash for the same value every time, it is a valid hash function. And last but not least, it is generally allowed for multiple input values to result in the same output value, the same hash. So called a collision. You should try to avoid these, but in general, you can't avoid it because the input size of value simply is possibly much bigger than the output set of values. So it's unavoidable, but you should try to avoid it, which plays a major role in deciding which hashing function to use. So based on these rules, a possible hashing implementation for grid point would be just return 42. It's totally valid, but kind of useless. But you map from an arbitrary value to a fixed size, which is totally fine, and it's persistent because you're always returning the same value. An example that's more realistic to actually appear in real life is something like this. You use the different fields, get their hash value, and then combine them using XOR. And like quick show of hands, how many of you have at some point implemented one of those functions that look like this or seen one of those in your code? Okay, that's about 50%. And now looking at this code, which opens a set, then creates all the grid points on the canvas from 100 by 100, and inserts the hash values of those grid points into the set, and then later on counts the number of unique hashes in the set. The input is 10,000 unique items. What would you guess is the output? What is the number of unique hashes generated by the hash function we just saw on the slide before? So possibly, the potential number of unique values is 10,000. And the optimal value of unique values is 10,000. So what would you expect? 100? Which is pretty bad, right? I mean, it should be 10,000, not 100. I mean, you want the optimal distribution in the space of possible values. Otherwise, you just look at the same row in your hash table all the time. So let's look at what this code actually does. Okay, so we have the grid point, the implementation of Hashable as we have seen before, and then the same loop accumulating those hashes. And if we run these, we do indeed get 128 unique hashes, which is pretty darn horrible. So in other words, we have a 100% collision rate. Every single value has a collision with at least one of the other ones. And they're actually distributed evenly, so you get like 128 divided by 10,000. That's the number of hashes you get, collisions you get per hash. So something is wrong here. And what's wrong here basically is that you're reducing the space of values by XORing these together. Every time you XOR a value in a hash function, at some point you have to inflate it again in the space of possible hash values. And that's not happening here. So let me get back here. So that's a 100% collision rate, which is pretty bad. We should be at 0%. It should be 10,000 unique hashes. So in other words, we could just have stayed with return 42 at this point. There's not much difference here. And if we actually look at some numbers, given that an XOR with a value in itself always returns 0, we can very easily forge a set of grid points which will all evaluate to the same hash. So just going like x equals 0, y equals 0, x equals 1, y equals 1, basically going the diagonal coordinate line, those will all fall on the same hash value. So if we add these to a set, instead of getting the expected green performance, we get an exponential, we get a quadratic performance because we're always doing a linear search in the bucket that the hash resulted in. And that's pretty bad, especially when your application is using Swift on the server, where you cannot control the input. So someone could be forging the values that they're sending to you in a JSON payload or just in like HTTP headers, for example, which results in a DDoS. So right now, Swift kind of has DDoS as a service it built in, which I think is pretty bad. So that's one of the things that's, I think, is wrong with Hashable, or at least less than optimal. The other one is that I think application developers like us shouldn't ever have to touch hashing. We shouldn't ever have to bother about how to properly hash. We should just have to like call a function hash, and it figures out how to do the actual complicated hashing logic, which then also is not only valid but also good. And the solution is to just not require users to do it for them. Which then also avoids the pitfall of many types requiring domain-specific knowledge. Like, for example, if you wanted to implement the hash value property for double yourself, you would have to keep in mind that for double and float, there exists -0, which, if compared to +0, always returns in true, but they differ in the bit representation. The first bit is set for the negative one. So if you don't do this, you get different hashes, which then evaluate to the same, to be equal, which violates the rules set up by hash value. And to make things even worse, the example code that I showed you with the grid point actually is Apple's sample code for Hashable. So, oh, I should actually show it on the screen. Yeah, that's not it. So I just copy and pasted the stuff from Apple's sample code. And this code, which is supposed to be teaching you how to implement hashing, basically has the worst case, or kind of the worst case, performance when it comes to hashing, which doesn't really help either. So, like, another different example of types which are difficult to implement hashing for a string, because every time you have some kind of normalization, which also is the case for negative and +0, you have to also keep this normalization for hashing. So for example, for strings, for UTF-8 strings, you have to first normalize the string before calculating the hash, because, for example, the German umlaut Ü or depending on how you type the stuff, is different. So if you just type the actual Ü key, you get a different string, like UTF-8 string, than if you typed option U followed by U, which uses the compound version of this, which is a different byte sequence, but should be the same. So there's lots of things to keep in mind, which I think we shouldn't have to bother with either. And then doing this wrong, we have the potential of like leading to DDoS when we're using Swift on the server. Fortunately, they fixed this for strings. So strings uses smart hashing algorithms, so-called SIP-hash, which has proper distribution. But still, for your custom types, you have to keep this in mind. So every time you put your own types into a dictionary set, you still have to keep this in mind. So it's not saving us really. And the same problem has been the case for PHP at ASP.NET, Ruby, Java, and Python, when in the 28th and 29th Chaos Communication Congress, there were talks exposing this weakness of hash flooding DDoS attacks. And the solution for this, which is kind of a workaround, is to randomly provide seeds to your hash function, which are like used as the initial values of your hash function, which is stateful. And a different problem is that you can exchange hashing functions. So for example, if you had to choose between using a fast hashing function and using a safe hashing function, which usually take much longer to compute, you might not want the standard library to have made the choice for you. You might want to choose yourself that for this particular project, I want a fast one because I own the input and I pretty much hope I didn't screw it up. But for this other one, which takes input from the web or from whatever else, I might want to go the safe path and take some safer, or maybe hopefully the default safe hasher. So the solution for this is to allow you to choose the type that's being used instead of like setting a default. And then last but not least, there's the problem of not being able to use different hashing strategies or hashing algorithms per instance. So you might want to have in the same application one dictionary which is safe because it takes input from outside, and one dictionary which is fast because it's somewhere in your bottleneck in your business logic. So it shouldn't be like a matter of type choice, but like actually injecting a specific hasher into your instance of set or dictionary. And that then also is the solution to this problem. So how do we do this? Well, basically the solution we should pretty much all know, because it's the same stuff that we do with NSCoder, or rather NS coding. We're using the visitor pattern. So when you implement NS coding for type, you don't implement plist or XML or JSON like generation. You just tell the NS coder, which was passed to you, to deal with X and to deal with Y, and that's it. You don't need to know anything about plist, or even know that there's like 3 different representation types for plist, like binary, JSON, and XML. Nothing of this is like leaked here and has to be on your plate to know about this. You just pass it and move on with your stuff. So what I would like to see is to have hashing look like this. You just pass X and Y to the hasher and move on. And at the same time, you're safe. You're not at the risk of making any mistakes. So thus the title of harsh visitors. And the way to implement this is to change Hashable or augment Hashable with an additional function, which is equivalent to the encode with coder, have a hasher protocol, which allows hashing of arbitrary byte sequences, and then also calculating the actual final hash value, because this isn't always like a one-step, because you're actually, if you have a huge structure or type structure, you're actually passing the entire structure to the same hasher. It's not like you're generating a hasher for the root and then for each child a different hasher. You generate one hasher in your dictionary and then passing it through the entire structure. And depending on for which children you call this hasher hash function, you actually specify where it goes in your hierarchy, just like it does for NS coding. And then come on. Then last but not least, there's an additional protocol called Hashable, which is kind of like a hasher factory, which is important because we want to seed the hasher so we can avoid attackers generating some kind of rainbow tables to attack our servers, because they always know what's the initial seed value of the hasher, so they can basically pre-compute, which is very intense for computation, but they can do it like over a week or whatever, and then once they have the results, they can then attack our server. By randomly seeding the stuff, it's basically fruitless to do so. So that's why you want the hash builder, because you can then, inside the build function, pre-configure the hasher, like passing a seed or something. And then grid point would look like this. This is how you would implement hash value for grid point. And I'm right now implementing this, and I hope to be able to have a pull request at some point for the standard library. And I would like, once this would be merged into the standard library, to then have a compiler warning for every implementation of hash value, which would urge you to switch to this kind of stuff. Or it could maybe even auto-generate this code for you. So, or with some kind of fix-it, maybe. So with these changes, we basically have solved these three problems. And now to show how like one of those hashers would look like, how you would implement a hasher, there's one semi-safe, semi-secure hasher. It's not cryptographically secure, but it's reasonably secure for most uses. FNV1A hash, where you can see the initial seed value, which you would randomly generate on the first start of the application and then pass to your dictionaries. And the actual hashing logic fits on a second screen. But this, again, this is stuff you wouldn't implement. This is stuff that the standard library would provide you unless you actually want to implement your own hasher for whatever reason. And by that, we then fix number 4. And like a very, very reduced, simple example of how, like, on a very high level, set would then possibly be implemented is you would have an additional initializer which take a hasher builder, which is then made part of the set. And before actually hashing an element that's coming in, you ask the hasher builder to build a hash, because these hashes are disposed after running. They're like very ad hoc types. And by that, we can then use multiple hashing algorithms per type, because we can choose them per instance of the dictionary or set, for example. And then figuring out the proper bucket would use the yellow highlighted code to, the yellow code is now equivalent to element.hashValue. It's a bit more verbose, but this is stuff you probably wouldn't have to write yourself as well, because it's hidden inside dictionary. And to be backwards compatible, you could implement this function as a default for every type that already implements Hashable. This wouldn't improve hash value at all, but it would at least not break your code. So it would be nice to have a warning then to remove the hash value and then remove this with a proper implementation. And then a use of this like custom-tuned, hash-tuned set would then look like this. So you would create a set of team members and pass it your proper fast hasher builder, which then results in a very efficient and fast set. If you want a particularly secure set, you would like initialize it with some secure hasher builder or whatever. And from there, basically, it's all the same as you would be used to using with a set. And then you have fixed the last problem. And to show you that I'm not just like making stuff up here, let's show the actual code running. So this is basically the code of the previous slides with the addition of an implementation of hashing for integers. This is stuff you also wouldn't have to write. Usually you would just write this stuff. Then you have the fn1h hash, the same code from below. And if you run this, you actually get 0 collisions, which is the stuff you would want. It's kind of lucky. There could have been like a dozen or something, but you would expect it to be very, very high in the uniques and thus very low in the collisions. And if you want to know more about this, there's a lengthy and in detail blog post about this with all kinds of additional information on different hashing strategies and what's the important parts of different hashing, like locality preserving hashing and cryptographic hashing, and why this would benefit. The code, however, isn't. The code is from an earlier state, so it doesn't match the stuff I showed here. I will update it, hopefully tomorrow. So yeah, thanks. And if you have any questions.
I think I don't need the microphone. Anyway, why do you need to pass the hasher by reference? That puzzles me really.
That's a very good question. So where's my mouse? There it is. Yeah, you mean this in out here, right?
Yes, exactly.
Yeah, well, the reason for this is that I chose to implement hashers as a struct. If I had chosen it to be like a simple class protocol, you wouldn't need it. But the consequence of using a class for hashers is that because you're generating those hashers ad hoc and you're disposing them afterwards. So kind of like with every call of hash value or whatever we're using to replace it, you would create a hasher on the heap. And that's kind of wasteful. I wouldn't expect hash to do an allocation. So by using a struct, I can just like pass a reference to the stack instance of hasher, which makes things a bit uglier, yeah. And to be honest, I haven't done any serious benchmarking yet. That's still something I have to do. But that's the reason, basically.
Yeah. Hasher is basically something that provides a hash, right? Where
it provides the hashing algorithm.
Yeah. So it's a function.
It is a two-step function because you need the accumulation and then the final, because some of those hashing functions.
So could you pass the hasher be just two functions that call each other, or do they? So you don't need to allocate it. That's it.
Yeah, but they're stateful, right? So it needs to.
Sure, you could pass it. You could pass that as a still recursive function. So just down. I mean, it will break because it's not there yet, but you don't have to have a reference.
Yeah. Yeah, I suppose there are a couple of ways to possibly make this nicer. I don't like in-out either, but I don't think allocating a hasher is a good idea either. I mean, if you look at the standard library, there's pretty much the only instances of classes are those special copy on write wrapper.
I'm not suggesting that you make a class and just that you make a free function that just calls itself tail recursively. Maybe one day you'll have tail recursion with all the app.
Yeah. Or one day you have like kind of Rust-like memory model in Swift, optional optimal memory model, but it's like Swift 5 or 6 or yeah, I totally agree. It's ugly.
I didn't quite understand why don't you make it a class if you want to pass it by reference?
Because classes are on the heap, and heap allocation is much more expensive than stack allocation. With stack allocation, you're simply just increasing a number, like number plus 1 or plus the size of the type. While with heap allocation, you actually have to like malloc would have to look in the linked list that persists the free regions in the heap memory, and then figure out the optimal one and do all kinds of bookkeeping. And you would then also have to do the freeing afterwards. So it's much more involved.
Right, so then that's the difference. So you don't need to do that if you pass a struct by reference.
Yes. But then again, because I'm returning a type erased hasher from the hash builder anyway. Oh, I didn't include the hash builder in here because we only need it in set or dictionary. The hash builder returns hashable, which already is required to return on the heap because it's type erased, because those hashes could be of different size. So maybe I'm over analyzing here, and I'm not actually saving anything. I'll have to do benchmarks for this. Yeah, but that's the reasoning behind it, at least.
Just a little remark. I think what wouldn't be possible with your solution would be to recompute the hash value. And I guess in some situations that might be useful.
Yeah, you mean like for example, returning a constant or something?
You have a very huge data class, whatever, and the hash calculation takes some time. And you would use it a lot of times. You would use it in a lot of dictionaries, whatever. Then it might make sense to compute it lazily and then store it for later use. If it's unimmutable.
Yeah, but I suppose then you could cache it at some other level.
Yeah.
So I'm not sure if enabling caching in the hashing API itself would be reason enough to let go of these other benefits of composability, basically.
It's just a remark.
Yeah.
I was just thinking about what I've seen about what people do with hashing.
Yeah. So it's kind of the same benefits you get from this design for hashing would also benefit description, for example, which kind of works the same way. And with description right now, you're allocating lots of strings, right? That's basically the talk that was also presented at UIConf yesterday, right? No, the day before. Yeah. So you kind of have the same idea here. Instead of allocating lots of temporary strings, which you then pass into string format or another print function, you could instead pass some kind of string builder, which would be kind of like a hasher in this case, to the description or print function, which then only ever allocates a single string because you're just feeding the stuff to the string builder. So there are lots of APIs which you could make much more efficient and also much more versatile, because, for example, you could easily exchange the string builder. You could exchange the string builder, which one that generates a UDF-8 string or that generates different encodings or JSON formatted output. You basically, the only stuff you're doing is the passing around of this object that deals with the actual logic. So, which is the entire purpose of the visitor pattern to begin with.
Another question. Do you think that the reason that it's not a really easy 1-0 solution might be the reason that Apple didn't expose it to us? That Apple wants to force us to think about and to decide it ourselves if there are different ways of implementing it, and if there is no 100% safe or no golden way to go, because it's always a trade between performance and accuracy, and so might that be the reason that they force us to think ourselves about the solution?
I would argue that this is the one button, it just works version. Because, I mean, you could even go as far as to auto-generate where is it? This part, which is much more trivial to auto-generate because you just you enumerate the different fields of your type and you just pass it to the hasher. And if you want to allow users or programmers to exclude certain fields from the hashing, you would have to add some kind of tag or whatever to these properties. And then the compiler would know to skip those ones for the auto code generation. So, well, I don't know. I consider this much easier for the user because the only stuff you're ever going to deal with is this one. All the rest is just making the stuff work for you. While with the version we have right now, you have to do all the work and you have to do it in there.
Yeah, but you are forced to decide whether you use a fast lossy
no, you don't.
Or
that's only if you want to pass one to it. If you, well, this is not.
I mean, right now we are forced to decide whether we want to use a lossy algorithm or not.
No, why should you? By default.
Because there is no, we can't use the built-in Hashable because it's private. It's a private call to, for example, the hash function for strings in Swift. We can't use the same hashing function because it's private.
Yeah, but that's the case with every single other function in Swift as well. It's not more private than other ones.
Yeah.
I think they chose to go this path because it makes it easier to transition from Objective-C because with Objective-C you're just bridging to the old call of hash. They just changed the name and added a value suffix to it. It makes it easier to bridge this, but even the bridging is rather simple to implement. I'm implementing it right now, and this part I've already figured out. The difficult part is that both set and dictionary actually are like double-headed creatures. There are enums which internally then have two different implementations. They can be a native set or a Cocoa set, depending on what's the value type, the element type. If the element type is an Objective-C class, you're going to get a different dictionary. And so it's a bit tricky because you have to make sure that the hasher is passed around properly. But I hope to be done with this, I don't know, in a week or something.